Well, we've introduced the gravitational force, and like any other force, it's like any force that you can apply to a free body diagram, like the dynamics that we were working with in Chapter 5 that you know and love. It's just another force in town, and it is the gravitational force. And it's responsible for the Kepler's laws, the 3 laws of planetary motion. And it's also responsible for particles to be bound to one another. The binding energy for stationary masses is equal to the negative g, mass 1, mass 2, over the distance between them. And the distance is from the center of mass of one to the center of mass of the other. We'd say that they're bound by this amount of energy, so you would have to take the positive value of this amount of energy in order to be able to separate the masses. Negative sign means this potential energy is taken to be 0 at infinite separation, and then as they get bound together, then they have a negative binding energy. Well, in Chapter 8, we saw that for every conservative force, there is a potential energy, and we can derive the force from the potential energy by taking the derivative, negative derivative of the potential energy function. So let's try that with this potential energy, this binding energy. If I take the negative derivative of this binding energy with respect to r, we would have this, negative ddr, negative g, mass 1, mass 2 over r. Negative 1 times negative 1 cancels out, and then we have the derivative with respect to r of g, mass 1, mass 2, r to the negative 1. These first 3, g, mass 1, mass 2, are constants. Take those out of the integral, and then we'll decrement the r to the negative 1 to get negative 1 r to the negative 2. And this is simply negative g, mass 1, mass 2 over r squared, which you recognize as being the gravitational force. So the negative derivative of the potential energy function gives you the gravitational force. Gravitational force is negative 2 because it's attractive. But what happens if one mass is moving around the other mass? Hence, it's not going to be bound as well because it's already got some energy, some kinetic energy, and hence it's not going to need as much energy in order to escape the other mass. It has more energy to aid in its escape. Let's see how bound it is. Well, we might recognize that for a satellite, if it's going more or less roughly in a circular orbit, the centripetal force would be provided by the mutual gravitational force between the central planet and the satellite. So we could say centripetal force, mass times v squared over r, is equal to the gravitational force, g, big M, little m over r squared. We can get rid of a little m on both sides, the mass of the satellite, and then we can get rid of one of the r's, and then take the square root of both sides, and we have that the velocity of a satellite in stable orbit is equal to the square root of our famous g constant, 6.67 times 10 to the minus 11, times the mass of the planet, or central body in this case, over the radius of the orbit, square root. That is indeed the velocity of a satellite in stable orbit around mass m. Let's use this to calculate the satellite's kinetic energy. 1/2 mass times velocity squared gives us 1/2 mass times, and then we square that velocity we just got. We get gm over r for that. So that is g, big M, little m over 2r. That's our kinetic energy. Hence our total energy for the moving mass is its kinetic energy, which we just got, gmm over 2r, plus its potential energy of binding, negative g mm over r at any particular point. This gives us a total energy of negative g, big M, little m over 2r, which happens to be a binding energy that is half of what we had for a stationary object, which means that because the satellite has some kinetic energy, it's not going to take as much energy for it to be able to escape the other object. And in fact, in a stable orbit, it only needs half that energy in order to escape, as opposed to being stationary. Consider a rocket trying to escape Earth's gravity. What speed would it need to escape? Let's look at this situation. Let's use what we just found out. Soon, right after launch, the rocket has some kinetic energy, 1/2 mass times initial velocity squared, and it's still bound to the Earth, and it's pretty much at the radius of the Earth still right after launch. So it has a binding energy of a negative g mass of the Earth, mass of the satellite over the distance between them, the radius of the Earth. So that's its initial energy. Its final energy is when it gets far away and it just barely escapes Earth's gravity. At that point, if it just barely escaped, then its final velocity would be 0. And if it has escaped Earth's gravity, then its radius must be more or less infinity. So this first term, with final velocity being 0 and the radius being infinity, 1 over infinity will give us 0 for the second term. So we just barely escaped. We have a final energy of 0. Everything we had was put in to trying to escape the planet. Well, it must be true then that our initial energy should equal our final energy, and our initial energy, 1/2 mass times our velocity, escape velocity from the Earth squared, plus our initial binding energy should equal our final energy, which is 0. We want to solve this for our escape velocity. Get rid of a little m on both sides. Solve this for the escape velocity, and we get our escape velocity is the square root of 2 times gravitational constant g, mass of the Earth over the radius of the Earth, square root. And that is indeed our escape velocity from the Earth. Now, if it were any other planet, it would be the mass of that planet over the radius of that planet, or any other large mass, it would be 2g, the mass of that over the radius of that, square root. So it's independent of the projectile's mass itself. It is independent of the direction of the projectile's velocity. So if you shoot it at an angle, you still need this escape velocity to get away. And hence, if you're trying to utilize as much energy as you can in your launch, what you'd want to do is shoot your launch at the Earth's equator, where you have the greatest amount of speed given you by the Earth's rotation, 1,000 miles per hour around the Earth's equator, as opposed to any other higher latitude, which is much less speed. If you can use the speed of the Earth spinning, that will give you less energy that you need in order to escape the Earth later on, because you can use that kinetic energy of the spin into your launch. Hence, the French shoot from French Guiana, which is closer to the equator than, say, from the country of France itself. This escape velocity is true for any object trying to escape from any large mass of radius r. Escape speed of a rocket. Let's calculate the escape speed from Earth for a 5,000 kilogram spacecraft. Well, we just found the escape speed should be 2g mass of Earth over the radius of the Earth, square root. That's 2 times 6.67 times 10 minus 11, 5.98 times 1024 for the mass of the Earth, 6.37 times 10 to the 6 meters for the radius of the Earth, square root. And this comes out to 1.12 times 10 to the 4 meters per second, or 11.2 kilometers per second. That's how fast anything would need to go, because it's independent of mass. Anything would need to go that speed in order to escape the Earth. 11.2 kilometers per second from the surface of the Earth. Determine the kinetic energy the rocket must have at the Earth's surface in order to escape the Earth's gravitational field. Well, it's going to need this speed, and for the 5,000 kilogram rocket, we're going to have 1/2 times 5,000 times 1.12 times 10 to the 4 meters per second squared. We're going to need 3.14 times 10 to the 11 joules to escape Earth. roughly the energy in a very small thunderstorm. 3.14 times 10 to the 11 joules for this rocket to escape the Earth. Let's try a different problem, an interesting problem. A treetop satellite moves in a circular orbit just above the surface of the planet, which is assumed to offer no air resistance. Show that its orbital speed v and the escape speed from the planet are related by the expression v escape equals the square root of 2 times v. Well, the escape speed we just found at some radius for the orbit would be the square root of 2g mass of the planet or the radius of the orbit at that moment. The orbital speed is, we found that earlier when we were looking at the centripetal force supplied by gravity, is the square root of g mass of the planet or the radius of the orbit. If I take the ratio of these two, the ratio of the escape speed over the stable orbital speed at that moment is the ratio of this square root over this square root, which is the g's are going to cancel out, the planet masses are going to cancel out, the radiuses are going to cancel out, and I'm going to just get the square root of 2. So v escape over the v of the stable orbit is the square root of 2. This is really cool. The escape speed is equal to the square root of the stable orbital speed that the satellite has at that moment. So if the moon is going around the Earth at 1 kilometer per second, which is how fast the moon moves, the moon needs to move the square root of 2, which is 1.414, 41.4% faster than it's doing right now in order to escape the Earth. If it starts moving out further and further, it's going to be slowing down, but at any particular point in a stable orbit, it's going to have to go 41.4% faster than what it's doing at that moment. Same thing for the shuttle. If the shuttle is going around the Earth at a smaller radius orbit, whatever speed it's doing at that moment, for it to escape Earth, it would have to go 41.4% faster than what it's doing in a already determined stable orbit. So this is a cool rule of thumb. If you ever find yourself in orbit around the Earth and you want to escape, you just need to go 41.4% faster and you can escape the Earth. Applying physics. NASA employs a method called slingshotting or gravitational boosting, gravitational assist, to add velocity to a spaceship as it passes near a planet. Consider a spacecraft moving with a speed of 10 kilometers per second approaching the planet Jupiter, which moves in its orbit around the Sun at an average speed of 13.1 kilometers per second. Find the speed of the spacecraft after this quote-unquote elastic collision with the planet. Gravity is a conservative force. This kind of collision, where the planet swings around the planet and gets that gravitational boost, is more or less an elastic collision. So if we had a spacecraft coming into Jupiter, hence looking like it's moving in the positive x direction here, with a 10 kilometer per second speed, and Jupiter is moving to the left, or as you're looking at to your left, I guess, 13.1 kilometers per second, we'll have an elastic collision between the two. And we know for an elastic collision that the sum of the velocities of one particle before and after the collision equals the sum of the velocities of the other particle before and after the collision. V1 initial plus V1 final equals V2 initial plus V2 final. In this case, our spacecraft is mass 1, so it's moving at 10 kilometers per second initially. We want to find its final velocity. Jupiter is moving at negative 13.1 in the opposite direction, kilometers per second, and that'll be its initial and final velocity. In fact, it's not going to change its velocity as a result of the satellite going around. We're going to be stealing a little bit of its energy, but it's not going to matter. Jupiter is so massive and it's moving so fast that it's got a lot of energy to give, and hence we're not going to hurt it at all by stealing just a little bit of its energy. Final velocity then for slingshotting around Jupiter would be a negative 36.2 kilometers per second. Free energy. So we don't have to build a rocket to get us up to that kind of speed. We just have to get us a rocket to get us to Jupiter, swing around Jupiter, grab that free energy, that free speed, and then fling us towards the outer solar system as we're moving really fast. We can make it to other places much sooner than we would if we didn't have this gravitational assist. Sometimes they'll slingshot around Jupiter, come back to Earth, slingshot around Earth, or slingshot around Venus, and every time pick up speed, pick up a lot of speed before we'll push it out to the outer solar system, to places like Saturn, Uranus, and Neptune. So in this case, it's going to gain more than 3 times its initial velocity by this slingshot around Jupiter. So that's a little bit of rocket science for you here in Chapter 13. This concludes our lecture on Chapter 13, and we will go on to Chapter 14, Fluid Dynamics. Take a look at some of the problems in Chapter 13, examples in the educreation example.